I'm Bruno de Batz de Trenquelléon. I want to talk about the hazes and the clouds in the solar system as the architects of the planetary climate. So I will present uh, especially my PhD work on Titan and the first results I have on Pluto, so a postdoc in the LIRA. So just to tell a bit of context, most of the atmosphere of the solar system has it. So with a wide variety, for example, we have some photochemical haze on Titan or Triton, and also Pluto. But we also have some organic ice haze on Uranus and Neptune, and also Pluto. So we will see that the haze of Pluto can be mixed between organic ice haze and photochemical one. And we can also uh, uh, look the other kind of haze, for example, haze from the surface with Mars when, for example, there is a global dust storm that produce global haze around the planet. And we can think about the Earth with the pollution that will produce aerosol and then some hazes. But we also can imagine some other haze, for example, produced by space debris or meteorites. For example, for Neptune, there is an hypothesis that say that the haze, part of the haze are produced by the ring of Neptune with a constant flux between the rings and the higher layer of the atmosphere. But there is also a huge variety of clouds. For example, we have a methane cloud on Titan. We have the water cloud on Earth and Mars with some cloud of CO2. We have the special case of Venus entirely covered by a cloud. But we have also we observed some cloud in the giant planet. For example, on Saturn and Jupiter, we observed some storm of ammonia with a lot of big clouds, and we have some observation of methane cloud on Uranus and Neptune, and we expect some H2S cloud deeper in the atmosphere. So and the question here is what are the effects of these hazes and clouds on global climate? So when we have a planet covered by hazes or cloud, the solar flux can go through this layer, but a big part will be reflected into the space or absorbed by the haze, for example. The haze can produce some scattering and produce a scattering of the solar energy into the atmosphere. And we also know that the cloud and the hazes will absorb the infrared flux coming from the surface or the deeper layer of the atmosphere and produce radiative cooling by emission of this flux. So also the cloud can interact with the atmosphere with a direct exchange with the atmosphere, for example, with the chemical compounds that will condense, and they can precipitate and produce mixing with the deeper layer of the atmosphere. So to understand and study these effects, I use Global Climate Model or GCM. So the challenge here is to build a virtual planet describing the real planet using the fundamental equation of the physics. So here we have the observation of Titan, for example, and I try to reproduce the observations with a model. So the most part of the GCM are composed of two blocks, one 3D dynamical core that solve the Navier-Stokes equation. So they solve the atmospheric circulation, the transport through the atmosphere. And on each atmospheric column, so in 1D, we solve the physical processes, so as the radiative transfer, the turbulence, or the microphysics. And when the planet has a surface, we also take into account the exchanges between the atmosphere and the surface. So today, most of the block into the GCM are coupled. For example, the chemical species are coupled with the radiative transfer that force the dynamics and the chemical species. And to understand the impact of the hazes and the clouds, we have to add some block into the GCM. So one block for the hazes and one block for the clouds. And the challenge here is to take into account all the physical processes, so couple these two blocks with the entire model. So it's what I did during my PhD on the Titan PCM, so the Titan the GCM developed here in Paris. And to do that, I implement a microphysical model in the GCM. So basically, we have the two equations that describe the evolution of the population of aerosols, so the haze, and one for the droplet population, so the clouds. Each population is subject to different physical processes, like the production, the transport with the sedimentation. For the aerosol, we take into account the coagulation to have two kind of aerosol, the small spherical one and the big fractal one. For the droplet population, we also have the sedimentation, and we only take into account the heterogeneous nucleation. So the cloud will condense with nuclei and condense into the aerosol. So there will be an exchange between the two populations, and the condensation and the evaporation will describe the size distribution of the cloud, the particle of the cloud. So the challenge here is that this equation are very heavy in calculation time, because we have they depend on the radius of the particle. So we have to solve this equation on each radius of the population. So in order to simplify that, we use a microphysical model in moments developed by Burgala et al. 2014 and 17. So the principle is we fix the size distribution. For example, here we have the size distribution of the aerosol and Titan. And we integrate this equation to study only the moment of the distribution. So we use two moments, the moment of order 0 that correspond to the total number of aerosol or cloud, and the moment of order 3 that correspond to the volume. So with the two equations below, we lose the dependency in radius, and we apply only this equation on the two moments. So it's we solve the issue of the calculation time. So it allows us to use a microphysical model into a GCM 3D model. So my first topic was Titan. So just to summarize, Titan has a dense atmosphere with a surface pressure about 1.46 bar and a surface temperature about 94 Kelvin. But here the interesting part is the composition of the atmosphere. So Titan's atmosphere has mostly nitrogen in it, with a few % of methane and some trace of hydrocarbons or nitride. And this is this composition that allow the formation of the hazes. So the methane coming from the lakes, so from the surface, will reach the upper layer of the atmosphere, will be dissociated with the nitrogen by the solar photons or the charged particles, and form a most complex set of molecules that will coagulate when they will settle and produce aerosol. So this this is this aerosol that produce this orange color of the Titan, opaque in the visible and transparent in the infrared. So one part of the photo-dissociated molecule will produce aerosol, and the other part will produce some hydrocarbon, more complex hydrocarbons or nitrile that will condense on the aerosol. So in the deeper layers, we have some clouds. For example, here we have pictures of methane cloud and Titan. And as I said, here the important part is that the cloud has formed on the aerosol. So the species will condense on the aerosol. So the first study after I did after implement the microphysical model in the GCM is I studied the Titan's ice cycle to understand the impact on the atmosphere. So above we have the extinction of the atmosphere in pressure and latitude, and below the corresponding temperature. So for both winter south and winter north. And we see here that the extinction is dominated by the hazes, and the haze will follow the stratospheric circulation and produce an enrichment of the winter pole in aerosol. And during the winter, so this accumulation will produce a strong cooling of the stratosphere because of the emission of aerosol during the polar night. So we see here that where we have the haze and the accumulation of haze, we have a strong cooling of the stratosphere. So we see the direct impact of the haze on the temperature. At the opposite, on the summer pole, the solar flux will warm the atmospheric column, and it will increase the latitudinal temperature gradient between the equator and the pole that will finally strengthen all the circulation. I don't show the circulation here, but in the model, we now reproduce the superior rotation of Titan about 200 meters per second, so very close to the observation. And it's the first time GCM reproduce a strong super rotation close to the observation. And it's a direct impact of the coupling between the microphysics with the radiative transfer. So the second study of my thesis was the methane cycle on Titan. So here we are interested into the cloud. So the methane, as I said, come from the surface. When it will evaporate from the lake, it will be mixed by the turbulence or the winds and produce a uniform region of methane, about 5.5% between 0 and 5 kilometers. And above, the methane will saturated, and it will produce a drop in the mole fraction between 5 and 25 kilometers. And in this region, the cloud will form. So when we study the formation of cloud in the GCM, so below we have the extinction of the cloud between the surface and 30 kilometers. We see in black contours circulation of the circulation of the atmosphere, and the cloud will form into the ascending branch of the circulation. So most of the time it will happen during the summer between at the mid latitude between 40 and 70 degrees of latitude. And this is the ascending branch that will transport the methane into the upper layer where the methane condenses. So it was a result already know that the methane cloud are formed into the ascending branch of the circulation, but it's well reproduced by the GCM now. So with the GCM, we can also study the mapping of the methane cloud. So here we have the opacity on the surface. We see that the opacity of the cloud is dominated by the methane cloud. We see some big cloud during the winter in the summer hemisphere, and in black contour, we have the precipitation rate above 0.1 millimeter per Titan day. And we see that the methane will precipitate mostly in the north where we have the lakes. So when the methane will evaporate from the lakes, it will saturate and will precipitate into the lakes and refill it. But another part will precipitate, for example, near the equator around the equinox. So it is what we saw during in 2010 during the North Vernal Equinox with a big precipitation event near the equator.
Question.
Yes.
So when you have precipitation, there is no clouds.
Yeah, it's because the big cloud we see in this map are produced around 20 kilometers, so they are visible. They are very visible, but the cloud that will precipitate are produced around 5 kilometers,
okay.
And it's mostly small cloud, not visible. So the cloud from at high altitude will settle, and after precipitate, it's why we can see some precipitation after the formation of cloud. There is a latence between the formation of cloud and the precipitation.
I have a question also. Like when Huygens landed, it seemed that the soil was like damp, liquid, from precipitation, I guess. But that would be before the rainy season in the aquarium. Do you have any idea? Like, was it not that damp, or was it already a little bit rainy, or was it from the previous year?
But here I just plot the higher precipitation rate.
Okay.
So we have some precipitation in also.
So you can have it everywhere.
Sorry?
So you can have precipitation everywhere.
Yeah, but mostly we're in the ascending branch, below the ascending branch of the circulation. So yeah, I don't really know if yeah. Because Huygens was near the equator at 10 yes south. So maybe it was an old a former precipitation. So the third 2D of my PhD was the Titan's polar cloud. So most of the observation we have from for Titans come from the Cassini mission. So between 2004 and 2017, during this 13 years of observation, we observe a lot of polar cloud, especially in the north. When we first saw the North Pole, we observed that it was entirely covered by a big cloud until 60 degrees of latitude. And after the equinox, this cloud disappeared. And just few years after, in 2012, we observed another polar cloud, this time at the opposite pole in the south. And this cloud was very constrained into the pole, so not above 80 degrees of latitude. So the question here is how this cloud formed, because the south pole, the south cloud was observed around 300 kilometers. So how this cloud formed so high, and what is their evolution? Is the cloud formed in the beginning of the autumn is the same as the cloud we observed in the end of the winter? So to answer this question, I first studied the temperature profile of the pole. So here we have the Sears observations of the temperature from Vinati et al. 2015 and 20. So in the north, so it's during autumn, the southern autumn and the northern spring. So during in the north, where the temperature raises as summer approaches, so it was expected because we exit the polar night, and in the southern autumn we saw a strong cooling of the south lower stratosphere that was expected, but as the winter solstice approaches, we saw the temperature increase, and it was the question why the temperature increased. So in the south is the strong cooling is here, and the temperature rising was here. So to understand that, I studied the temperatures, heating and cooling rate, and the extinction from the GCM. So the GCM in the square with on the observations. So the model would reproduce the temperature variation with a strong cooling during the first half of the autumn, and the temperature increasing after. So to understand that, we see that the strong cooling is produced by two factors. The first one is we enter in the polar night, so we have a reduction in the solar heating, but we also have a strong increase in the extinction here. Produced by the haze, and this is the haze that will produce the strong a strong cooling by radiative emission that explains the strong cooling we saw on the observation. And after that, we have a constant period of for the temperature, and as the solstice, winter solstice approaches, the subsidence of the circulation will intensify, so that will produce adiabatic heating that will dominate the radiative cooling. So it's the blue curve here. We saw that we observed some planetary rates, and sometime it will dominate the radiative cooling, so that explains why we have the increase of the temperature. So after that, we can study the polar cloud on the GCM. So here we have the cloud for the North Pole and the South Pole. We see, for example, for the South Pole that the GCM predict formation of cloud in the first half of autumn around 300 kilometers. So as we saw in 2012 in the South Pole. After that, so this cloud is produced mostly by the strong cooling and the subsidence that will produce an enrichment of chemical species into the pole. And after that, the cloud will drop in altitude and stabilize around 100 kilometers and stabilize until the end of the winter. So it's in the North Pole, we see that we can explain why we observed a big cloud in 2006 at the end of the winter pole. After the equinox, this cloud will disappear because the temperature will increase while we exit the polar night, and the circulation will there will be an inversion of the circulation that will enrich the opposite pole of the chemical species. So we can focus on the species that condense into the cloud. So around 300 kilometers, the cloud is composed half of HCN and half of C6H6. And while it drops into the atmosphere, some other species can condense. For example, below 200 kilometers, we have some HC3N that can condense. And below 100 kilometers, we also have some hydrocarbons as ethane or acetylene. So it was, just a last study on Titan. We can also look at the impact of the haze and the cloud on the surface. For example, we have the surface opacity and the surface temperature, and we see that the surface temperature will follow the haze cycle. So the opacity is dominated by the haze, as I said, and we see that the temperature is the opacity has a direct impact on the surface temperature. So now I will present my work on Pluto. So Pluto is the atmosphere is different because it's a tiny atmosphere with a surface pressure around between 0.1 and 1.1 Pascal, with a surface temperature around 40 Kelvin. But the composition of the atmosphere is similar with most part of nitrogen with trace of methane and carbon monoxide. So when New Horizons in 2015 observed Pluto, we observe an extensive haze present all around the limb. And with a vertical extinction above 200 kilometers. This haze is structured in many layers between 1 and 10 kilometers. And we observe that we have more visible, this haze is more visible at high phase angles with Rayleigh scatters that suggest some very small particle around 10 nanometers. But we also observe a large high to low phase brightness ratio that suggests bigger particle above larger than 100 nanometers. So maybe suggest some fractal particles. So directly we can compare the atmosphere, the hazes of Titans and Pluto, because we will have some fractal and spherical particles. So here I have a little game. Where is Pluto? Where is Titan? I don't know if
maybe Titan on the left and on the right.
Yeah, it's right, because for Titan we have the leakage haze layer that is very characteristic of the atmosphere of Titan. So good job. So the question of the Pluto haze is what is the mechanism of formation for the haze? Because there is two scenarios. One, it would be an organic haze like Titan. The point here is both atmospheres are similar. The Pluto's atmosphere is similar to the Titan's one above 400 kilometers, so where the haze formed on Titan, and the observation are quite similar, so we can suggest that it's the same kind of haze. But another scenario was proposed by Lavas et al. 2021 because they find that we need twice higher haze formation efficiency to reproduce the UV extinction observation below 200 kilometers. And the other point is that Pluto's upper atmosphere is much colder than Titan's. So they suggest that the haze will be formed by the condensation of hydrocarbon, because we see here that most of the hydrocarbon condense in the atmosphere of Pluto. So to answer this question is require microphysical models. So it's the topic of my postdoc I started last October. So I implement in the Pluto GCM the same kind of microphysical model adapted for Pluto, and I try to answer several questions. So, for example, which kind of haze dominates in the atmosphere of Pluto? What explains the vertical and latitudinal variation in the temperature profile? Or what is the properties of this haze? So the first results I obtained, so here I implemented the microphysical model into the GCM, and I did some 1D test. So here in dashed black, we have the observation from New Horizon. In black, we have the temperature profile of the model before I implemented the microphysics. So only the gases was in the model with parameterized cooling to reproduce the observation. And when I implement the microphysical model, I obtain the color curves. So we see here that the A's will have a strong impact into the temperature profile with here strong cooling, strong heating. But the fact is we can reproduce the same vertical gradient of the observation. So it's a good point. If we just parameterize the optical properties of the A's, maybe we can match the observation. And the other point is if I change the latitude, I change also the temperature. So we expect that when we do this test in 3D, we have some latitudinal variation. So also I obtain, for now, I just implement the the photochemical A's, but I don't implement the condensation yet. And I obtain A's composed of spherical aerosol around 50 nanometers and a fractal one near the surface around 0.3 micrometers, so close to the observation. So if we look at the extension of the A's, so in a dash black we have the observation again, and in black only the model with gaze, and in red with the A's, and we see that the A's explain. We reproduce the extinction profile with the A's, which is 100 more intense than the gaze. The other result here on the right, it's the heating and cooling rate. We saw that when we had the A's into the model, we have a heating and cooling rate 100 stronger than the gaze. So we can expect that if we double, for example, the amount of methane in the atmosphere, the temperature will be not impact because it's the A's that dominates the temperature profile and the heating and cooling rate. So another study for the future, we know that Pluto surface is covered by different and several terrains. So with the microphysical model, we can maybe explain the different kind of terrains with and study the deposition of the A's in the surface. So it will be another study with the microphysical model. So just I want to talk about a little of Uranus and Neptune. So this time we don't have surface. We have a different kind of atmosphere composed mostly of H2 with helium and a few % of methane. And some studies of Irene et al. 2022 propose an aerosol distribution for Uranus and Neptune. So this between 10 bar and 0.01. So they suggest that the Uranus and Neptune atmosphere are composed of a cloud layer of H2S ice between 5 and 7 bar. Above, we will have some photochemical hazes between 1 and 2 bar with the formation of methane cloud, and above an extended stratospheric haze layer composed of photochemical aerosols. And just for Neptune, they need an additional layer of methane ice particles at 0.2 bar to explain its increased reflectivity. So Daniel Toledo in Madrid did created a 1D microphysical model for Uranus and Neptune, and to study the haze and try to reproduce the observation from the HST and Voyager 2. So they suggest that the haze will be particles likely photochemically produced via methane dissociation with haze particles around 0.2 micrometers, so similar to the size of Pluto's haze. And but the fact is the haze formation timescales exceed 30 years, so that indicates that microphysical processes alone cannot explain the observation of the seasonal variation observation. So they suggest maybe it will be dynamics or other kind of haze that will produce this seasonal variation. And it's their last study is about the methane cloud. They expect some methane cloud around between 1 and 2 bar for Uranus and Neptune, but with cloud droplets around 100 micrometers, leading in a high precipitation rates. And this is this high precipitation rate that prevents the formation of a thick optically dense cloud layer, and they said that it explains why when we observe Uranus or Neptune, we don't see a big methane cloud or a cloud layer, a constant cloud layer. And after the cloud formed, they will precipitate and re-evaporate and give back the aerosol into the atmosphere, producing a secondary aerosol layer observed in the observation. And so they can explain also this observation. And last study was did by Milkarek et al. 2024 to try to understand the impact of the haze on the temperature profile. So they call that the energy crisis of Uranus and Neptune because today, there's no model that can explain the temperature profile of the stratosphere of Uranus and Neptune. So Milkarek et al. Did study with a 1D radiative conductive model to see the impact of this haze. So when they combine the effect of the aerosol layers with the thermospheric conduction for Uranus, they can reproduce the temperature profile, but not for Neptune. So they suggest again that can be a dynamics phenomena or maybe a fractal aerosol because they use only a spherical one in this model. So it will be also a next study for the microphysical model coupled with GCM. So just to conclude, we saw with these 4 examples that even we have different kind of planet, we have some similarity in the haze, but also some different. We have a different kind of haze, a photochemical haze or ice, organic ice haze. And to conclude, we saw that the hazes can vary significantly depending on their formation processes, that subtle differences in their formation mechanism can have an important implications for their resulting properties and their role in the atmosphere. And we saw that coupling a microphysical model of haze and clouds with a GCM allows us for studying and understanding their role in the global climate of planet. For example, here we are now able to explain the radiative cooling of Titan's stratosphere. We can map the Titan's methane clouds and analyze the formation of the polar clouds. And we have some initial explanations for the thermal profile of Pluto, Uranus, and Neptune. And we can also think about ongoing projects on early Earth, for example, by Benjamin Charnay at the LIRA. And we can expect and think of a future project. For example, we want to use our microphysical model on Pluto to study the atmosphere of Triton, and we can adapt this kind of model for the gas giants or the exoplanets. Thank you for listening.